In this chapter, I would like to share the layout experience for inductor. Actually, inductor, capacitor, and resistor, all of them are called passive devices. Why? Because they don't provide any kind of power gain. Yeah, that is the most fundamental requirement for passive devices. If you would like, if the device would like to be an active one, then it needs to provide some kind of power gain. For example, for any kind of device, you can view it as a black box. Then you can check the input port and the output port. Only if the output power is larger than the input, then it can be called an active device. But for resistor, capacitor, and the inductor, it has only one port, right? So it means the output port and the input port will be exactly the same. Then no way you can have such kind of power gain, because the resistance will consume some power to reduce the power gain less than 1. That is the definition for passive device. So you can see one of the possibilities to be an active device, just like transistor, right? The input port here, the output port there. So for output port, it can derive, it can transfer some of the power from your VCC to the output. In this way, the output power can be larger than input power to make it as an active device. All right. First of all, the output port and the unless it is a battery. Otherwise, if the output port and the input port are exactly the same, there's no way to get power gain larger than 1. Okay. So for inductor, what are the most important parameters? First of all, the inductance, and then the quality factor, the resonance frequency, and for our on-chip inductor, we pay much attention to the chip size. Anyway, what is quality factor? The Q factor actually, it is the energy stored by the device divided by the energy loss per cycle. It means the more power loss, the less quality factor. That's it. But why? Inductor will consume some power. Yeah, very simple. According to its parasitic resistance. That's it. And for on-chip inductor, as I mentioned, we pay a lot of attention to its active area, because usually for such kind of RF circuit, the passive layout area usually is much larger than the active device area. That's a big problem, right? So hopefully we can reduce the area for active devices. Usually, I mean for inductors. So how to reduce the chip area for inductor becomes a very important idea for RFIC layout. And for such kind of usually we have on-chip planar spiral inductor. That is the easiest, but the quality factor is no good, and also the size is not scaled with the process evolution, right? But that is some kind of demerit. But keep this in mind, even for traditional parallel plate capacitor, yeah, the size doesn't scale with the process evolution either. However, if you make it from horizontal one to the vertical one, as I mentioned already, the vertical parallel plate capacitor can be scaled with the process evolution. So we solve the problem for capacitor. But how about our inductor? Is it some kind of insoluble problem? Let's wait and see. All right. This is some kind of simple models for inductor. Yeah, you can see this is the main parameter for inductance, but you will have some kind of series resistance or parallel resistance. It's up to you to use this model or that model, but according to the Q factor in series connection, you will see here, right? So it means what? The larger series resistance, the smaller Q factor. So in such kind of simple model, you had better try your very best to reduce RS. However, for your circuit, if it is better to use such kind of parallel connection, then according to the Q factor, RP is here, right? So how to enlarge Q factor? You need to enlarge RP. Okay, it means you need to enlarge the parallel resistance. Because they are connected in parallel, so it means what? The larger RP means the less current it conducts here, it consumes here. It means the smaller power will be dissipated, will be wasted here. This is the reason why the larger RP, the larger Q. Okay, as you like. So again, to apply this serial model or to apply that parallel model is all up to you, up to your circuit. All right. And if you need to consider also the parallel capacitance, then this is some kind of model for you. But again, for Q factor, then what might you consider both capacitance and resistance or not? Here you can see, yeah, never mind with CP or not. RP needs to be larger to get larger Q. That's it. Okay. Yeah. Anyway, for the other consent, you can see Q equals the imaginary part divided by real part. Imaginary part composed of inductance and capacitance, right? And how about the real part? Again, the resistance. That's it. Allow me to show you what kind of inductors you can have for our chip. First of all, you can have such kind of active inductor. Active means, see, it uses such kind of op-amps to compose the so-called gyrator. Yeah, and what is the function? To reverse the phase shift. Okay, for inductor, you have SL, right? And for capacitor, you have 1 over SC. So this is J omega L, and that is J omega C. That is minus 1 omega C. So the only difference between inductance and capacitance is the positive phase or the negative phase. So to reverse it, we can make such kind of capacitor to become inductor. Bingo! That is a quite simple, quite easy idea through the help of the so-called gyrator. Yeah, these two op-amps compose the gyrator to reverse the phase of the capacitor to become an inductor. That's it. That's it. Yeah, piece of cake, right? But what is the problem with gyrator? Why you guys, I think, never see such kind of inductor? The good of gyrator is also the bad of the gyrator. Why? Because with op-amps, the operation frequency will be seriously limited. That's it. That's it. So it means what? With such kind of active inductor, the operation frequency will be really, really low. Never mention about gigahertz operation. That's too much. Even for hundreds of megahertz, I think it's some kind of mission impossible. All right. So for our RF circuit, we don't touch such kind of active inductor. Then we have spiral inductor. Later I will show you the layout. However, the other choice is to use bonding wire as the inductor. For bonding wire, actually, here, that is some kind of rough estimation. 1 millimeter bonding wire can provide 1 nanohenry inductance. That's it. So after packaging for your whole chip simulation, right? You need to consider, such kind of bonding wire and keep this in mind. So if you have long bonding wire just like this, it is done by purpose to have such kind of long bonding wire for what? To get large enough inductance for RF circuit. That's it. That's it. And the Q factor, because it is composed of metal wire, the resistance, the series resistance for such compounding wire actually is much, much less than on-chip spiral inductor. According to the model I show you, the serial model I show you, the RS is quite small, right? So it has very high Q. And also the cost is very small. It's very low. Why? Because if you apply such kind of spiral inductor, usually it will occupy a lot of chip area. Chip area means what? Money, right? And how about bonding wire? The overall cost actually is much less than large chip area for such kind of spiral inductor. So it has very high Q and the cost is rather low, but the disadvantage disadvantages are process variation and high parasitic capacitance, because it is simply above the chip office. So you need to face some kind of parasitic capacitance between the bonding wire and the circuit or substrate below it. Okay, and here, that is some kind of two-dimensional view or three-dimensional view for such kind of horizontal spiral inductor. Usually we have such kind of square layout. Got it? But to reduce RS, again, we need to have, because for inductor, you will see it has two terminals, right? Right? So this is the first terminal, and how to connect the second terminal? You need to have such kind of underpass connection. Usually, for the main body of such kind of spiral inductor, we will use the top metal, right? Because the top metal is the thickest. Then it means what? The RS, the series resistance, will be the minimum. 这个最顶层的金属，因为它最厚啊，所以它的那个串联电阻会是最小的。好，不过因为电感它有两个端点啊，所以第一个端点在这边啊，第二个端点呢，你只能走地下道嘛，拉出去嘛，所以怎么走地下道？因为这是通常我们是用最顶层的金属。所以我们这个地下道就用第二顶层的金属。That's it. So for the connection of the first terminal, we can use the same top metal. But how about the underpass connection? it needs the help of the next to the top metal layer. For example, in 0.80 micron, this is M6. So how about the underpass? Usually M5. That's it. Okay. Yeah, but it will cause some big issue, big problem for you, because here are some kind of overlap between M6 and M5. So you will have some kind of parasitic capacitance here. Such kind of parasitic capacitance along with the inductance, it will reduce, it will lower the self-resonance frequency very, very much. Okay. Later, we will go back to discuss such kind of impact for self-resonance frequency. Then this comes some kind of cross-sectional view. And as I mentioned moments ago, we use the top metal for the main body of the spiral inductor. So the first terminal is here, but how to connect the second terminal? We need such kind of underpass connection. This for 0.18, that is M6, and this is next to M6, so that is M5. Okay, that's it. That is the usual case. Yeah. So again, if your top metal is M5, then for underpass connection, you use M4. So that is, you need to have such kind of vias to connect M4 and M5, blah, blah, blah. All right? Yeah. Again, why we use top metal? Because that is the thickest, right? 我们会使用最顶层的金属，就是它最厚啊，所以它的那个有效串联阻抗会是最小的。That's it. And according those mechanisms, as I mentioned, how about the Q factor? Q factor means the overall energy you can store divided by energy you will dissipate, or the device will waste. Okay, so to reduce the wasting of the power, it means to increase the Q factor. But what kind of mechanism to waste the power? Two kinds mechanisms. First of all, metal losses. Yeah, according to skin effect. Yeah, I mentioned already. The higher frequency means the more resistance you need to face. So you need to pay much attention to skin effect, and sometimes also proximity effect. Yeah, anyway, I mentioned both when in chapter 7 or something for wiring. Oh yeah, anyhow. And the other one is subject losses. Why we have such kind of subject losses? Simply because for such kind of spiral inductor, according to EMI interference or Lenz's law, 冷次定律. Okay, yeah. Anyway, the variation of electronic field will induce some kind of magnetic field, and also the variation of the magnetic field will in turn induce some kind of electrical field, blah blah blah. Okay, anyway, the electrical field variation along such kind of spiral inductor, you don't expect DC current inside the inductor. No. To have any kind of inductance, you need to carry AC current. Got it? Inductor is for AC operation instead of DC operation. So the AC operation of the inductor means you will have many kind of variation of the electric field along such kind of metal line, right? So as I mentioned, according to Lenz's law, the variation of electrical field will induce some kind of magnetic field. So for such kind of magnetic field, right, something like this, then the variation, you have variation, I have also variation for such kind of magnetic flux. Okay, so the variation for such kind of magnetic flux penetrating into the subject, you will have two kind of disturbance. One is eddy current. Yeah, the electric field induced by the magnetic field will have some kind of circulation current. We call it eddy current, 涡流. And the other one is the induced potential here and there won't be exactly the same. So some of the current will flow from here to there, and the other one will flow from there to here. It depends on the potential. Which potential is higher? If higher here, then flow over there. If higher there, then flow back here, blah, 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 blah. All possible, all possible. So for such kind of disturbance in the substrate, never mind caused by eddy current or displacement current, they both consume some power. All right, and where does it come from? I mean, the power to be wasted. Again, the electric field variation to induce the magnetic variation, then intense the magnetic flux variation cause such kind of eddy current, displaced current. So what is the origin of the energy? Yeah, from the very beginning, the energy from the electrical field in the inductor. That's it. Okay, so the original energy actually comes from inductor itself. So the energy dissipated here, the energy wasted here actually comes from the energy stored in the inductor. That's it. So it means what? The more energy wasted here means the less Q, right? Because the more energy wasted, the less Q factor. This is the reason why you need to pay a lot of attention according to such kind of substrate losses. OK， 不论如何哈。因为我们有所谓的那个逆电动势的冷测定律啦哈，所以那个电场的那个改变会衍生磁场，然后磁场因为它将会穿透到我们的那个substrate 里面去嘛哈，那电场改变，磁场会跟着怎么样？磁场改变又会衍生一大堆的那个电场出来，哎呀，反正鸡生蛋，蛋生鸡的都有了哈。这种的话我刚有解释过哈，它会产生那个涡流啊，或者是会产生那个移动电流啦。不管你涡流或移动电流，天下没有白吃的午餐嘛。这些衍生出来的电流跑来跑去就是会撞晶格，然后产生热量，会把那个能量消耗掉能量从哪里来最源头不就是从那个电感本身来的吗？从它的那个电场的改变衍生磁场，磁场再衍生这边的电场，巴拉巴拉巴拉。所以你这边所浪费掉的任何能量，其实都是来自于电感本身啦。那你讲的讲是 Q factor 就是你的储存能量除以你浪费的能量浪费的能量越多，那你的 Q factor 就会越低，就这样子。天底下没有白吃的午餐。That's it. So we need to try our very best to reduce not only the energy wasted inside the inductor, but also the energy wasted here. I mean, in the substrate. In this way, we can increase the quality factor. Okay, this is some kind of induced flux. Yeah, penetrating into the substrate. 这张图就可以让各位知道这些衍生的那个磁力线它会穿透我们的基底了这是一个比较好看的那个 3D 的那个图形。Okay, so allow me to show you such kind of substrate losses. How to prevent such kind of substrate losses? One of the easy ways is to remove it, right? So you can see, but you may see, hey, how to remove such kind of subject? Nowadays, I think the easiest way is to get help through MEMS。我们现在有标准的 MEMS 制程了，所以台积电、联电都有。所以你用 MEMS 制程就可以把记忆拿掉。Anyway, TSMC, UMC nowadays, they provide standard MEMS process after chip fabrication to remove anything you like, including substrate. Okay, you can see after the removal of the substrate, not only the inductance is increased, but also the Q factor, right? You can see the dashed line is for which substrate, and the solid line is for after substrate removal. It is a very strong proof that substrate losses actually contribute a lot to Q factor. Okay, if you pay enough attention to such kind of substrate losses, if you reduce the substrate losses, then the Q factor will be increased very, very much. However, nothing is free. You need to pay the price for a substrate removal. If you wouldn't like to pay the money for such kind of removal, what we can do? Later, I will show you some of the other ways. Okay, with standard process, you don't need to get any kind of help from MEMS. Later, I will show you. Yeah, anyway, again, this is some kind of three-dimensional view to tell you such kind of flux will penetrate into the substrate and induce a lot of AD current or displacement current, blah, blah, blah. Okay, that is some kind of three-dimensional micro photo for you to refer. And this is some kind of three-dimensional plot. Again, please pay attention to CS. CS is a parasitic capacitance between the top layer and the underpass. Okay, and I told you already, such kind of CS actually it will reduce the self-resonance frequency very, very much. That is really bad. Okay, CS here. Yeah. Anyway, anyhow. For such kind of inductor model, we have many kind of models. And for this model, we call it lumped hybrid pi model. Okay? What is you want? Only this. And for all the others, actually, you hate them very, very much. Anyway, anyhow. This one, as the series resistance actually has some kind of very much impact on Q factor. You had better reduce it. And again, how about CS? It will reduce the self-resonance frequency. That is also very bad. You had better reduce it, blah, blah, blah. And this is some kind of ideal model. And allow me to show you the three-dimensional model for some kind of one-to-one mapping. You will know who causes what. 这个是理想的 model， 然后底下这个是一个 3D 的那个图可以给各位一个1对1的对应啦。你知道原流头占有主啦每一个参数是什么物件造成的原流头占有主您自己去看。Okay, and for IS, as I mentioned, for such kind of serious resistance, we have better reduce it. And the most important one is the so-called skin effect. And as I mentioned again and again, the higher frequency, the smaller thickness, right? So the more impact for such kind of skin effect. That's it. That is the skin depth. All right. The higher frequency, the smaller skin depth. It means the effective cross-sectional area for current conduction will be reduced, and you will increase ice. That's it. All right. And yeah, this is what I would like to show you. After simulation, you will see the higher frequency, the more serious resistance here. Oh, this is quite bad. And according to such kind of flux, okay, that is the coil, the rotation of the coil, and according to such kind of AC current, blah blah blah, you will see according to our right hand rule, what is the orientation of the induced field according to such kind of current. You will see it is in this direction. Okay, in this direction. All right. So if you have a look at for such kind of right-hand rule, right, the induced field look like this, look like that. Okay. So it means what? It will be cancelled here and enhanced there. It depends on the rotation of the current. Okay, so it really means that according to such kind of AC current, or briefly speaking, skin effect, for inner coils, one side the current density will be reduced, at the other side it will be increased. Is it good for you? No. Okay, the impact will be increased from outer coil to inner coil. That's it. 我跟各位强调一下你用弗莱明右手定则啦，你的那个电流如果是这样子转就像这个样子那么依照你的右手定律你去看你来看那个靠中央的这一些那个导线有没有依照弗莱明右手定则律快对不？它的那个衍生出来的那个场，它的方向是朝这个地方所以你看以目前的这个电流方向来看它内部 AC current 所造成的因为它碰到金属会反过来嘛所以你可以发现它们在这个地方互相抵消，在这个地方互相加成意思是什么？你的那个电流密度在这个地方会变得很低，在另外一边会变得比较高，意思就是说内部的导线在那个 AC current 或是广义来讲这 skin effect 的影响之下呢他们的电流会偏向一边，不会均匀的分布这个就很惨了。越靠内部这个现象会越明显，也就是说越靠内部的话，那么那个有效导通的那个截面积会越来越小，它的阻抗会越来越高请各位务必要继续做电。Okay, briefly speaking, for the coil, the inner coil will get more impact through such kind of AC current or the so-called skin effect. It means what? The effective cross-sectional for current conduction will be reduced from the outer to the inner. Okay, so it means what? The RS from the outer to the inner will be increased very much. Keep this in mind. Okay, then to the for some slides later than this, I will show you how to face that kind of challenge. Okay, later I will tell you how to face such kind of challenge. And this is some kind of simulation. And again, you can see, this is the current density. The hotter, the more, the cooler, the less. Okay? So you can see, as I mentioned already, the impact from the outer coil to the inner coil, you can see for the inner ones, they face more impact, more they face more impact from the eddy current, from the skin effect. Okay, you can see here, especially here, you can see, right? Almost all the current crowded here, as I mentioned already, right? So it means what? The RS here is smaller. I mean for outer coil and for inner coil, because most of the current crowded here and to the other side. Wow, the current density is really small. You can neglect it. So again, for the cross-sectional area for current conduction, actually it is reduced very much, and it means RS increase very much for inner coils. Keep this in mind. Keep this in mind. It is a big problem for you guys. But if you think such kind of problem becomes your opportunity, if you can deal with such kind of problem, then bingo. You solve the problem, you can create some kind of new idea, maybe only for inductor layout. You can apply the patent, then get royalty from all the others. 吃苦甲当作是咧吃补啦哈，就是我头甲恁讲过哈，那个越往内靠哈，那么那个集污效应或是涡流效应会越来越明显了哈，所以 RS 会越来越大，因为你的电流会越来越集中在某一侧 ，OK 啊。一般人看到这个说，哎呀，恐怖啦，恐怖就会死啦吼！我跟你讲，勇敢处理这个问题，你若再想出一个新的办法，去解决这个问题，你就再申请专利啊，对不对？对 inductor 来讲，我想专利绝大部分都是跟那个布局有关，而不是跟设计啊。反正它就是个 device 嘛，对不对？啊，对 device 来讲，你的专利大概就是个布局而已啦，没有什么其他更好的办法了啊。如果你想得出来，你就是世界 number one。那么你可以申请专利，你可以跟其他所有的公司，包括Qualcomm、联发科去抽你的那个叫人头税啦哈，去跟他们抽 royalty， 你的报喜啊，一世人让我们做赶快。Okay, again, I think I mentioned this already. You need to reduce CS here, right? The underpass. The parasitic capacitance between the underpass and the top metal, blah blah blah, reduce it. Yeah, and this is what I would like to tell you. Yeah, this is the substrate, the metal loss. Okay, yeah. Anyway, no, sorry. This is for substrate loss. Okay, and the other one is for metal loss. Okay, you can see it depends on the coil radius very much. So you can fine tune the coil radius to consider to get the best performance for your inductor. Later I will show you one of the papers how to fine tune the coil radius. Then consider both impact. This is for metal loss, that is for substrate loss. You need to consider both to get the best performance. I mean to get the maximum Q. This is the definition for Q vector I mentioned already. And some kind of simulation result with one of the model called wideband model. Yeah, you can see. Yeah, with the multiplication here, you will see for such kind of simulation, yeah, this one looks good, but for the other parameter, it seems not so good. What we can do, actually, to have for the multiplication, then for both parameters, they fit each other very well. Anyhow, I'm not any kind of device guy, right? I'm a circuit designer, so I pay no attention to this. If you are any kind of device guy, then maybe you can try to modify the model, and after measurement, you will say, hey, look, my model is more accurate than the others. Then you can publish the paper. Wow, piece of cake. Congratulations. 拍起来，因为我是迄个电路设计者，我唔是迄个元件设计者哈，所以对这种元件来讲，我无啥物兴趣，我嘛一点仔都唔知啦哈。你若是专攻元件的话，你就使去改 model 只要你量测出来的结果证明你的 model 比别人强，你就可以发表论文。哎呦，恭喜哦，恭喜哦。Okay, yeah. Anyway, again you can see CS appears again and again, right? It shows up again and again. So it means what? It's really, really important for the operation of inductor. Again, what is CS? That is the overlapped parasitic capacitance. The parasitic capacitance between the top metal and the overpass. Okay, here. Underpass. Yeah. So you can see for the other model, it included such kind of RP, then more accurate between the simulation result and the measurement result. That's it. Yeah. Again, I pay no attention to this. If you are interested, you can get online. Maybe you can find even better new papers to get even more accurate model for your inductor. That's it. That is what you can do, but not for me, okay? Again, I'm a circuit designer. And also, I didn't pay any attention to RF circuit design, so forget about it. If you do RF circuit design, maybe you need to pay attention to this, okay? Then let's go back to the layout for inductor, because this class is for IC layout. All right, so how to do a good enough layout for inductor? Allow me to show you three major kinds. This is some kind of solid inductor ring. It doesn't make any sense. Why? Because you don't have any kind of open in the middle. Then the induced flux cannot go through the middle of the inductor. It means the inductance will become really small. Don't do any kind of silly layout like this. You need to have opening in the middle. Okay. Then with guard ring, what is the function of guard ring? To limit the flux don't go out. Okay, don't go out the inductor far away. Yeah. Then all the flux will be limited inside the guard ring. In this way, you can increase a little bit of the Q factor. Yeah. Never mind, the guard ring is complete or partial guard ring. Both works. So allow me to show you the result. You can see from here, yeah, with guard ring, the red line, the Q factor is increased. Okay, that is what we would like to get. And this is some kind of real micro photo for you to refer. For typical coil inductor, it's really hard to implement on chip, right? So usually we have such kind of planar spiral inductor. Anyway, the Q factor is no good. Yeah. Never mind, you have this is guard ring, right? So the inductor is inside the guard ring, and you have some kind of internal opening in the middle. Anyway, some other talented guy have such kind of three-dimensional inductor. This is the overview, and allow me to zoom in for you. It looks much similar to such kind of discrete coil inductor. So what does it mean? Usually the Q factor for this will be much better than that. But again, nothing is free. If you would like to have such kind of three-dimensional inductor on chip, usually you need to get help from MEMS. That means you need to pay for it. You need to pay for the fabrication cost for MEMS. And then how about the shape for such kind of planar spiral inductor? For the simplest, we have such kind of square layout pattern. If you would like to pay more attention, then you can have octagon, or even you can have the best circular. Okay, the circle layout, the circular layout usually achieve the best Q factor. Why? Simply because it doesn't have any kind of sharp turns. All right, so it doesn't need to face any kind of current crowding impact. Then it means the RS will be reduced. In this way, Q again will be increased. That's it. That's it. So overall, you can see, briefly speaking, the Q factor for the circle layout is the best. Then octagon, then hexagon, then finally the square. Actually, for such kind of planar layout, square inductor gets the worst Q factor. But why we still use it? Simply because it is the simplest for layout. It's up to you, I don't care. But if you have time, my recommendation is octagon. Good enough. Don't try your very best to have such kind of circle layout. First of all, according to Q factor, no much difference between or among this, and that. So, to my opinion, octagon layout will be good enough. Since the difference between them, I mean the difference for Q factor among them, actually is not so much. You don't need to spend a lot of time for such kind of circle layout. However, the other problem is some of the process some of the process don't allow such kind of circular layout. Forget about it. Yeah. All right. Again, you need to have such kind of hollow, 中空的. It means you need to have some kind of opening in the middle. Yeah, otherwise the inductance will become really, really small. All right. In general, for such kind of on-chip spiral inductor, the inductance is smaller than 10 nanohenries, and you need to pay a lot of attention for such kind of spiral inductor because they usually occupy a lot of chip area. The Q factor is no good. Blah blah blah. Oh, and also, if they are too close to the other circuit, it will induce a lot of noise interference for the circuit. So you need to keep them far away enough. Otherwise, at least you need to provide some kind of guard ring to protect the other circuit from the inductor. So you can see guard ring is not only good to reduce the noise for the other circuit, but also it can increase the Q factor a little bit, as I showed you moments ago. All right, and also you need to pay attention to noise coupling because the flux will penetrate right into the substrate. It will cause a lot of disturbance in the substrate, but for the whole chip, everybody share the same substrate, so you will cause a lot of noise coupled to the other devices or the whole circuit. Pay attention to that. Then allow me to show you, this is a very good idea. We call it tapered spirals. As I showed you moments ago, let's go back. Here, right? What I told you, according to such kind of simulation. I told you, from outer to inner, you need to face more current crowding phenomenon. Okay, so it means the current will be crowded even more. I mean, in inner coil than outer coil, right? So in this way, you can see the current is crowded here. That is some kind of big challenge, big problem. But if you have different logic thinking, then you will say, hey, look, the current to the other side is really, really small, right? So you can simply forget about it. Under such kind of circumstances, we can reduce the width for the inner coil. Then it comes out such kind of new layout pattern. We call it tapered spirals. You can see the width of the coil reduced from outer to inner gradually, right? In this way, for the same layout area, you will have more turns. It means the inductance will be increased. Or with the same area and the same inductance, then it means what? The turns of the inductor will be reduced, and then you will have larger opening in the middle to let the flux penetrate into the substrate. In this way, you can also increase the quality factor. So with such kind of tapered layout, you can either increase the inductance per area, or you can increase the Q factor for the same inductance and layout area. Why not? 所以我头甲你讲过哈，食苦甲伊当做是食补啦哈。有人看到他拄仔迄个电流模拟分布有无哈？外口诶较均匀，愈我内底诶越靠其中的一边，就讲哎哟可怜哦，那 RS 会增加，咱就足可怜的诸如此类有无哈？哎呀，不用太烦恼嘛，你就把这个困难当做是一个挑战的机会啊，对不对？既然越靠中间那么它的电流越趋向其中的一边，你就把另外一边干掉就好了。因为另外一边承载非常少的电流，那干脆就忘了他们吧。所以有了这个新鲜的想法，有这个有创意的想法，那么我们就可以把那个 inductor 它的那个每一圈的那个宽度由外向内逐圈递减，那就变成所谓的 tapered spiral。有这种概念之后呢，各位可以想，同样的面积，你可以转更多圈如果你中央的 open 是一样的话，转更多圈表示什么？你的那个 inductance 就会更高不然的话就是同样的面积，同样的 inductance， 那你就不需要转那么多圈。不需要转那么多圈的话，那么中央的开口就会开得更大，让你的 flux 更容易穿进去，你的 Q factor 就会越高就是这样子。所以呢，吃苦改动作是咧吃补把那个把那个什么电感它的那个线宽从外围逐次递减向内围的话，由外圈递减到内圈的话，那么你可以说在同样的那个面积底下，你要么就可以增加你的那个电感值再不然你可以增加 Q 值。 Why not? Okay. Yeah, anyway, allow me to show you this. For different layout of the for the same area, you can see the quality factor increased from square, hexagon, octagon, all the way to circle, to circular, right? That's it. Yeah, but again, no much difference. You can see my recommendation is this, right? For octagon, actually the Q factor is very close to circular, but much better than square. So why not? According to layout complexity, I think for octagon layout, yeah, the effort is about the same as square, but much simpler than such kind of circle layout, right? And anyway, the Q factor is very close to the circular, so why not? And the other problem is, even you would like to spend a lot of time for such kind of circular layout, some of the processes simply don't allow you to have such kind of circular layout. So forget about it. Again, my recommendation is this for octagon. Okay, good enough. Please don't be too lazy to have such kind of square layout. No. Because the Q factor, I think the difference is too much. Okay, you have a significant difference in Q factor between the square and the octagon layout. So please, that is a fundamental requirement for you to have such kind of octagon layout for spiral inductor. And here I would like to share some kind of paper related to layout optimization for this guy from Peking, Beijing. I have no idea what kind of affiliation. If you are interested, Google online. Okay. Yeah. What Miss Guo would like to have? He would like to try how much the width for the coil and what is the opening in the middle, and how about the spacing between all those coil lines. For such kind of 3 parameters, he would like to do optimization to get the best Q factor. That's it. So according to this paper, the Q factor can be increased by 5 to 8. Wow, why not? If you have a look back here, see, even for the circular, the Q factor is less than 6. So an increase of the Q factor by 5 to 8 is huge. However, please pay attention to that. The paper here, the environment for this paper and the simulation for this plot actually are totally different. So don't be too happy. Okay, later I will show you some of the result for such kind of Q factor improvement. So from the beginning, he would like to do some kind of simulation. Okay, and after simulation through such kind of commercial products, HP ADS, Sonnet, microwave office, along with a free software, Aesthetic, to my memory provided by Berkeley Wireless Center, blah, blah, blah. Okay, he would like to focus on the inductance, the peak value for Q, the peak value for frequency, and the resonance frequency for all those 4 parameters. And this is some kind of simulation between the simulation and measurement. Okay, you can see even with the commercial product ADS and compared to free software Aesthetic. Free means what? You can download Aesthetic online. Maybe you need to submit it in some kind of application, and after that, you can get the free software. Okay, so let's see which one, between ADS and Aesthetic, which one will provide you the closer result to the measurement. You can see 0.4 is closer, the difference. Or you can see here, even closer. And how about here? See, only 0.1 in difference, but for ADS, 1.3 in difference. Wow. Never mind for inductance, peak Q factor, peaking frequency or resonance frequency. All of them will show that Aesthetic provide better result than ADS, then why you wouldn't like to pay money for that? Simply get free software called Aesthetic. Good enough for such kind of simulation because for all the result it wins. It is closer. The result simulated by Aesthetic is closer to the measurement than ADS. So the author would like to apply Aesthetic for such kind of layout optimization. And again, 3 parameters for optimization. The inner core size, the opening in the middle, okay, T. Then the width of the wire, W, and the spacing between wires, S. All right, let's go for this. First of all, you can see, never mind, you have rectangular layout or circular layout. Actually, they are quite close to each other. That is for the first simulation. So the author decided to apply rectangular layout for optimization to make his life easier. If you would like to focus on circular, then the layout will become much more difficult than the rectangular one, right? So forget about such kind of circular. Anyway, I would like to say, first of all, no much difference between the rectangular and the circular layout. And also that the second reason is the tendency look very much similar for rectangular or circular layout. So it means what? If you have some kind of optimum layout pattern for rectangular inductor, then similar condition will be held for circular inductor. It means the optimum solution for this will be more likely to be the same optimum for circular inductor or very close to the optimum. So why not? 不论如何，就是说，这个作者蛮细心的哈，就是说他先做方形跟那个圆形的那个布局，然后发现，哎呀，他们两个差不多吗？再来趋势看起来也很像吗？所以呢，他就决定用方形来做他的那个优化的那个基础，他不去做圆形，因为圆形太难搞了，他不想花那么多时间了哈。因为两个的结果差不多，而且趋势看起来都一模一样嘛，所以各位可以猜得到哈，就是说，如果你是用方形的布局来得到最佳的那个解的话，那么把它的结果应用到圆形的布局，应该也差不了多少吧？即便不是最佳，也是非常接近最佳的 solution. So why not? The effort will be reduced very much for rectangular spiral layout than circular one. Okay, here from the beginning, he would like to figure out which is the best for inner coil size. See the T, right? So here is the best. Okay, yeah, so what is that? Around 120 microns. But for the others, actually not so bad. For example, this one. How much? 80 microns. About the same. Okay, so don't touch this or that. That means, yeah, the inner opening, okay, for only 20 micron or only 40 micron. Actually, they both are too small, and you can see the peak Q is the peak Q factor is much less than all the others. All right, so don't touch 20, 40, or even 60 or here. Yeah, so forget about all those 3 smaller ones. Then you can focus on the big one. But you cannot say, oh, the bigger the better. No. If you have a look at 120 and 130, you can see, yeah, 120 wins. Okay, the Q factor is better for this than that. Okay, let's go. And then with the same inner opening, yeah, internal opening. He would like to change the width. And you can see who wins. Here, that is the best for 8 microns. Okay, but anyway, I would like to point out that it depends on the process very, very much. Don't apply this for all. No. For each process, you need to do similar simulations to find the optimum value. Never mind for width, for T, or for spacing S. You need to do it by yourself for each new process. Don't apply this optimum value for width to all the other process. It doesn't make any sense. OK， 你唔若試著看到這個看一個影，生一個囝，你講，哎呀，這個人模擬出來哈，8 micron 是最佳的 solution， 所以你就以後你的那個布局，那寬度哈，那個線寬都是8麥。拍攝哈，因為你所使用的製程跟它可能完全不一樣，所以你要重新做模擬啊。OK, finally, he would like to show you this. From the turns, 幾圈啊哈 from 1 turn all the way to 8 turns, you can see the width, even for different turns, the optimum width is different. From 8 micron all the way to 2 micron, okay? And this is the spacing, and that is the inductance. The more turns means the more inductance. And overall, you can see the Q factor, and all this is very close to Wi-Fi. Wireless communication, blah, blah, blah. You can see from here to there, yeah. Maybe you'll say, hey, look, for larger inductance, the Q factor becomes much smaller, right? That is the tendency. You need to pay for it. But if you have a look at this with optimization and without optimization, you will see a big difference, right? Here, if you complain, the Q factor here is no good, please have a look. Without optimization, it is almost zero. But with optimization, we can raise it, we can increase it from maybe around 0 all the way to 5.01. So this is the reason why the author claimed that the Q factor can be increased from 5 to 8 here. Okay? From maybe around to more than 10. That's it. So that is the power of knowledge. If you have patience and innovation, you can do anything different and innovative to make the best result, just like the author of this paper. So this is some kind of very simple conclusion. Yeah, the optimization sequence is, first of all, to make the optimum T, then the optimum W, finally the optimum space. And overall, the Q factor is improved by 5 to 8 for this paper. Okay, you can do the same thing by yourself for the other processes. I promise you, after optimization, similarly, the Q value will be increased very, very much. And allow me to show you some of the other layout patterns. For example, stacked inductor, right? It has not only one layer, but 2 layers for the inductor layout. In this way, we can increase the inductance by maybe over 300%. However, nothing is free. Q factor will be reduced by about 50% according to their simulation or experiment. Okay, but why we would like to have such kind of stacked inductor? Simply because we can reduce the area, okay, for money saving. That's it. Then another new layout pattern called 3D miniature inductor. That is from Professor Chen Liu's lab 啊，从我老师，这是我学弟妹他们发明的啦。Okay, they have a look at this only 2 layers, right? They would like to expand it from the top metal all the way to the bottom metal. In this way, the inductance will be increased substantially. And among layers, you need to have some kind of phase shift. Don't overlap them. Why? If they are overlapped directly, then the parasitic capacitance will be increased. So you need to have some kind of horizontal shift a little bit. Now, for example, my wire fit your space, and your wire fit my space. That's it. To reduce the overlap area between adjacent layers, that is the way to enhance the performance. 哦，这是我头家啦哈，我学弟学妹做的啦。好，那就是啊 ，in the corner， 别人用2顶，就会使增加 inductance。要讲大家咧讲啊，我所有的迄个 layers 拢用来做 inductor layer 啊，那么当然就可以大幅增加它的那个电感值了哈。不过相邻2层中间一定要有一些那个位移啊，就是讲你甲看哦，我的线对着你中的迄个间隔，有无？不会直接跟上层的那个上下层的金属直接叠在一起啊。同样的道理，你的金属线就正对着我的中央的间隔哈。那这样的话就可以大幅减少那个相邻2层之间的那个电容值啊哈。这样的话做出来效果会比较好。Okay. Anyhow. Similarly, a stacked inductor, this one will increase the inductance very much, but the Q factor is expected to be lower. Nothing is free, you need to pay for it. So allow me to show you the measurement between the for L and Q between the traditional planar or spiral inductor and the newest miniature 3D inductor. You will see, it's really amazing. If you focus on Q factor, you can see, wow, the Q factor is even higher than the planar spiral inductor. And also that it can operate at much higher frequency here, right? The high frequency performance actually is much better for such kind of 3D inductor than the planar inductor. Okay, maybe for lower frequency band, its performance is a little bit worse. But nowadays, humankind focus very much on high frequency operation than low frequency operation, right? So we pay much attention to this band. Okay, it's much more important than the low frequency band. And also according to the inductance, you can see 3D inductor can provide much better inductance than the original planar inductor. If you compare the 3D inductor to the stacked inductor, you will see the Q factor is reduced a little bit from such kind of, this is for stacked, right? See, the square one for stacked, okay? However, again, for higher frequency band, actually the Q factor is improved for 3D inductor than stacked inductor. And how about the inductance? Again, here, you can see the 3D inductor is much better than stacked inductor for such kind of high frequency band. And also you can see the self-resonant frequency is much higher from here to there. You need to be careful after self-resonance frequency. Here it is inductor. After that, it becomes a capacitor. Okay, so it means what? 3D inductor can survive to much higher operation frequency than the stepped one. Wow, it's really amazing. It's really amazing. Okay, and to my memory, my professor applied patent for this, and this is the first patent he transferred to the industry. For how much? To my memory, yeah, half million NT dollars. Okay. Wow, that is the first technology transfer happened to my professor's lab. Not related to IC design, no, related to IC layout. Again, that is the power of layout patent. For circuit patent, my professor's lab had a lot of much more patents for IC layout, for IC design than layout. But the first technology transfer related to layout instead of design. You can see the layout pattern is much more powerful than circuit. OK， 借我记忆所及哈，我老板刘教授哈，他实验室第一个技转，事实上就是这一个东西。OK， 多少钱？50万台票尔啦，足俗的，因为这是第一本技转嘛。现在技转我看没有几百万是没有办法打趴的。不过不论如何，就是说我老板他是那个类比 IC 设计的一把手，结果呢，他第一个技转，他有一头拉苦的那个IC 设计的那个专利有没有？但是他第一个技转居然不是设计专利，而是布局专利。各位就可以知道布局专利的重要性远远高过设计。为什么？因为布局的专利很难想得出来，而且呢，布局的专利我跟各位讲过，法官用眼睛看就懂了啦。你的3D 本来是2D 你就可以把它打趴，就这么简单电路法官可是完全看不懂的啦。OK， anyway, I told you again and again. For the patent related to layout, it is not only much powerful but also much easier than for the judges. Okay, in the court, they can tell the difference about such kind of layout patterns, but they don't know what is the difference among circuit designs. That is what it will be much easier for you to win such kind of patent. You can sue each other very easily. Okay, let's go further. According to symmetry, the more symmetry, the better performance. Not only for the others layout, even for the same for inductor. Again, the more symmetry, the better performance. You need to make it by yourself. So, for example, this is some kind of center tape inductor for circular inductor. Okay, if you cut it through, it will be symmetry to the first terminal and the second terminal. I promise you, according to such kind of symmetric layout pattern, the performance will be better than asymmetry one. 这个是那个对电感有两端嘛，对不对那么你第一端跟第二端，各位从中间一切就是对称的那我跟各位打包票，越对称的布局，它的效果越好你们可以自己把它画一画，然后去吹或是去模拟有对称性的那个布局，它的效果会超过非对称性的布局。And for the other one, if you would like to have some kind of center tape inductor, just like this, okay, it has 3 nodes. In the middle, you will have some kind of a tape out point. Usually, you have such kind of a center tape inductor for transformer layout. When necessary, allow me to show you. This is one for you to refer. Anyway, anyhow, again, you can see in the middle, to the left, to the right, they are symmetrical. They are symmetrical for your first terminal and the second terminal, right? And where to put the middle terminal, the tape out point, the tapered point, anyway, the tapping point, sorry, yeah. If 50% to 50, 50% here, 50% there, then in the middle, okay? In this way, the layout can provide you the best performance. Then let's focus on the operation of your inductor, single-ended or differential. For the same inductor model, for single-ended excitation, you have your input here and the AC grounded to the other terminal. Then you will see this one disappeared. You only have this left. Okay, and how about differential excitation? You have positive input here, negative input there, so you can see the current flow from here to there or reversely. Okay, is up to the potentials, higher here or lower here. Okay, anyway, anyhow, you can see according to the current flow. See, yeah, for example, yeah, positive here, negative here. Then you can see R and R connected in series. Then you have 2R. The same C and C connected in series, but serial connection for capacitor will reduce the capacitance by 50%, right? To increase the capacitance, they need to be connected in parallel instead. So for such kind of differential excitation, you can enlarge, you can double the resistance. Very good to reduce the power wasting. Okay, and also because it is connected in parallel with L. Okay, for these 2R. And how about CN? How about the parasitic capacitance? It is reduced by 50%. Bingo. Okay, for such kind of parallel model, this one is increased. Good for power wasting, to reduce the power wasted here for parallel model, right? And to reduce the parasitic capacitance. It is good to increase the self-resonant frequency. Okay, so you can see, yeah. From this is for single-ended, and that is for differential excitation. Okay, for the same circular, the square one, the pink square ones, from here to there, you can see from single-ended operation to differential operation, the Q factor is increased very much. And for the same single-ended or differential operation between circular and square, you can see not much in difference. Again, circular is better, a little bit better than square, but not too much. So my recommendation is still octagon or a bit overall or a bit the best for you. You don't need to waste a lot of time for layout, but the performance is very close to circular. Okay, yeah, that is what I would like to mention that. And how about the temperature effect? Because the inductor is made of metal, the higher temperature means the free electrons will get more collision with the lattice. So the more collision, it means the less conductance. It means the more resistance and more power will be wasted for R, right? And it means the Q factor will also be reduced. That's it. So again, the higher temperature here, right? From the lowest to the highest, you can see Q factor is reduced all the way. So yeah, hopefully I convince you. The higher temperature, the lower Q value. That's it. Okay. And here is some kind of very good layout example from Berkeley Wildlife Center to my memory. Yeah, and for the students in such kind of top one, almost top one RF lab, they do such kind of layout. How about you? I don't think you think yourself are better than the students there, right? For such kind of the best students on earth, they do such kind of, again, octagon layout and also symmetrical layout, right? They pay a lot of effort for such kind of good layout. How about you? You need to do the same thing. So again, that is the fundamental requirement from me. Okay, I hope all the students after my teaching will do such kind of good enough layout. Again, symmetrical and symmetrical octagonal layout pattern. Okay, and this is some kind of simulation. You need to they did such kind of simulation through acetic. They composed the free program acetic. They simulate all those inductors with acetic. But if you would like to simulate it through the help of acetic, you need to know the thickness of your substrate, the epsilon of your substrate, everything. Okay? Yeah, anyhow, you need to make it by yourself. And this is some kind of model they used. This model, the first model and the second model, after measurement, you can see the second model is closer to the measurement result. Never mind, from such kind of Smith chart of such kind of Q factor. That is for S11 Smith chart, and this is for Q factor. Anyhow, the second model is better than the first model. Again, I'm not any kind of device guy. If you would like to get any further detail, please go back to read the papers by yourself. Okay, and then why we need to have such kind of inductor, accurate model, good layout for inductor, because it is used substantially in RF circuit. For example, this is some kind of high frequency oscillator. It needs two inductors. Okay, the better inductor layout, the better performance, the better anyway, you can get better performance for such kind of cross-coupled oscillator, not limited to oscillator, even for LNA, for mixer, blah blah blah, all of them. The better inductor, the better performance for all those RF circuits. All right, then I would like to tell you how to enhance the Q factor for such kind of on-chip inductor. You can apply the so-called PGS. Yeah, patent ground shield. What's that? This is a much better explanation. I mentioned moments ago with guard ring, the flux will be limited inside the guard ring, right? But the flux still penetrate into the substrate, and then it will induce some kind of eddy current, displacement current to waste the power, and the power wasting means what? The Q factor will be reduced. So how to stop such kind of flux penetrating into the substrate? Very simple. We can have such kind of metal shield to the bottom. What do I mean for bottom? You can use the bottom metal to be the shield. Okay, and the pattern is really fixed. You need to have some kind of fixed pattern for such kind of ground shield. So we call it patterned ground shield, PGS. First of all, the metal for shielding needs to be perpendicular to the wire of your inductor. Okay, they need to be orthogonal to each other. Got it? 最重要为什么怎么称就是那个 patent 的一个地的遮蔽哈，原因是在于说，它的那个样态是固定的哦，你做 shielding 的那个走线跟你 inductor 本身的走线一定要正交，一定要垂直 ，OK？ That is the definition for PGS. Again, the wires for shielding and the wire for inductor needs to be perpendicular or orthogonal to each other to provide the best shielding and also to reduce the parasitic capacitance between each. That's it. Yeah. So allow me to show you some kind of real photo. To the top, that is spiral inductor. To the bottom, that is PGS. And allow me to zoom in this portion for you. You can see that is the edge of the inductor, and you can see for the metal knives for shielding, actually they are perpendicular to the inductor knife. See, that is really important for you. That is for the inductor knife, and that is for shielding. You can see they are perpendicular. They are orthogonal to each other. Keep this in mind. In this way, you can reduce the parasitic capacitance very much to increase the self-resonant frequency. Got it? Yeah. So again, this is for guard ring, right? But to make it even better, not only you need the guard ring, but also the PGS. Okay, in this way, the Q factor will be much better. Okay, that is the PGS structure. Anyway, for advanced processes, you need to pay attention to the fill factor, right? If the fill rate becomes too low, then DRC will show something wrong. How to compensate for such kind of metal fill rate? You need to fill some kind of cubics, even inside the inductor. Okay, but for such kind of filling, they need to overlap each other. I mean, from the top to the bottom, they need to be aligned to allow the flux, penetrate into the middle opening to the bottom. Okay, this is no good because the flux has no way to penetrate the inner opening. It is no good for filling. Yeah. Anyway, anyhow, for such kind of MF metal fill, it is used to solve the field density problem. The field density problem you need to face during DRC check. Okay, and you need to do it, but what is the consequence? Anyway, the Q factor and the self-resonance frequency will be reduced a little bit. So allow me to show you the performance comparison with metal fill and without. You can see the inductance is reduced a little bit by 10%, and also the self-resonance frequency is reduced from here to there, also 10%. Okay. Or maybe sorry, the inductance is reduced more, but the resonance frequency is reduced by 10%. Okay, and how about the quality factor? And again, reduced by about 10%. Okay, you can have a look for the circle one, right? Only with PGS. Okay, if you have not only PGS but also metal field, right? PGS and MF, you can see, yeah, the Q factor is reduced. Okay, and overall speaking, 10% in reduction for Q factor. Yeah. Anyway, anyhow. Why we would like to have such kind of PGS? Because the Q factor will be increased substantially from regular layout. With PGS, the Q factor will be increased a lot. Okay, and also it can reduce the subtract noise coupling because we have the bottom metal to stop the flux penetrating into the substrate. So no noise coupling happens for such kind of substrate. All right. But anyway, with PGS, especially PGS with metal field, you will reduce the self-resonance frequency. It means that above it, again, the inductor will become capacitor. That's it. Okay. If you would like to enhance the Q factor even further, then you can make the inductor stand up. It becomes a vertical instead of a horizontal one, right? But how to make the horizontal inductor stand up to become a vertical one? Sorry, again, you need to get help from mains. Okay? If you would like to know the detail, please learn something according to mains. You will know how to make it. Right now, I'm your layout professor instead of MEMS teacher. Sorry for that. I have no time to tell you the truth, all the truth, okay? Then this is some kind of microstrip inductor layout. I think all the same, right? For two of them or a single one, and we center taped. All right, and symmetrical to both sides, similarly to each other. Okay, then I would like to tell something about on-chip transformers. Wow, keep this in mind. On-chip transformer is not for energy transfer. No. That is for some kind of signal transformation instead of energy transformation. For example, maybe you need to enlarge to amplify the RF signal, right? Or you would like to match the RF signal, blah, blah, blah. You need such kind of transformer on chip. However, don't expect you can transfer the energy from here to there. No, because the Q factor for such kind of wires, the inductor for the primary part or for the secondary part, actually the Q factor is too bad, right? So the energy transfer from the first port to the second port actually is really small. Don't expect on that. All right. Then how to do such kind of on-chip transformer layout? Yeah, piece of cake, right? For example, you have the primary inductor in the middle, and you have secondary inductor to the top and to the bottom. Then you will get such kind of mutual coupling coefficient K as large as possible. In this way, maybe the K factor will be close to 1. Perfect, 100%. But what is the problem? The Q factor for all those will be really poor, and also the parasitic capacity is really huge. You need to face the challenge. Okay, the self-resonance frequency will become very low. Maybe this is no good for RF circuit. Even so, what is my recommendation? Don't pay too much attention to K. No. Don't try your very best to make k as close to 1 as possible. No. Close to 1, enough close to 1 will be good enough. That's it. Yeah, don't make it perfect. Okay, so my recommendation is what? Only one will be, only one layer will be good enough. Okay, so primary here, secondary there, good enough. We don't need the third layer. Okay, yeah, even in this way, k can be maybe close to 0.8 to 0.9. I think that is good enough. And also that between them, you need to have, again, some kind of shift. All right, my wire feed your space, your wire feed my space. Okay, that is the definition for shift or wire shift, to reduce the overlapped parasitic capacitance. That's it. Okay, yeah. So this is some kind of model for such kind of on-chip transformer. Usually, because that is practical, so the parameter k is less than 1. All right, you need to pay attention to such kind of serial resistance and also port-to-port and port-to-substrate capacitance. Yeah, to reduce the resistance, to reduce the capacitance, will enhance the overall performance of such kind of transformer. So, for example, you can have such kind of tapered transformer, right? One to the outer and the other one in the inner. In this way, you can have very low port-to-port capacitance, but also the K will become really low. So you can have the other one, interleaved transformer. As you can guess, they are quite strong coupling between each, right? So the strong coupling between those two transformers can increase the K value, but it also increases the port-to-port capacitance, right? So finally, you can have stacked transformer. For this or that, you need to have only one metal layer, the top layer, to do layout for both inductors. For the primary and the secondary inductors. But for stacked transformer, you need 2 layers. They are overlapped. Okay? In this way, you can increase the K very, very much. But again, the port-to-port or the port-to-substrate capacitance will be increased also. Okay. Again, nothing is free. To increase K, you will also increase port-to-port and port-to-substrate capacitance. Again, how to reduce such kind of port-to-port capacitance? Shift, wire shift. That is what you need to consider. And why the port-to-substrate capacitance is also increased? Because for this and that, they only use the top metal, right? But for stacked transformer, you need to have 2 layers, the top one and the next to top. And the next to top one layer is close to substrate. In this way, the port-to-substrate capacitance will be increased. 天底下没有白吃的午餐哈。如果你要增加你的那个 K 值的话，你可以让那个一次侧跟2次侧的那个电感完全叠在一起呀，所以你需要2层的金属哈。那么这样的话呢，它的 K 值可以做到非常高，接近 0.9， 但是 port-to-port 的那个杂散电容还有 port-to-substrate 杂散电容都会增加哈。那 port-to-port 没办法，因为有上层跟下层嘛，所以我刚刚讲过哈，你要有位移，也就是说第2层它要对准第1层的那个空隙啊，第1层对准第2层的空隙啊，这样子做的话，我们可以再稍微压低一下 port-to-port 的那个杂散电容哈。 不过 port to substrate 杂散电路没办法，因为你使用2层嘛，所以你上面这一层是用 top metal， 然后底下那个是top metal 下一层嘛。OK， 好，那既然是 top metal 的下一层，那当然靠 substrate 就会比较近啊。人家前面这2个都只是用 top metal 而已嘛，所以他们离 substrate 比较远，所以没办法不管你怎么搞，这一种 stack transformer， 他们 substrate to port to substrate 的那个杂散电容都会比较大啦，这是没办法的代志啦。Okay, then we have some kind of variations. For example, if you would like to have some kind of spatial movement, displacement, sorry, yeah. For example, the top metal and the second to top metal, yeah, for the primary inductor, the secondary inductor, they need not to be fully overlapped, right? You can have some kind of displacement, horizontally, vertically, or diagonally. All right. In this way, the mutual inductance, yeah, the parameter K will be reduced, but the port-to-port capacitance will also be reduced. It's up to you. You can have such kind of trade-off. However, to do some kind of analysis, I think is truly hard. Okay, so yeah, that is some kind of trade-off. Just have a read, have a look by yourself. Nothing is ideal. Okay, you need to do some kind of trade-off. Anyway, according to our taped, interleaved, stacked, you can see according to chip area, according to coupling effect, self-inductance, or self-resonance frequency, you need to do you need to do trade-off. Okay, you cannot get the best among all the parameters. No. If you would like to get the best K here, right? Then you will see the self-resonance frequency will become very low. Why? Because the port-to-port and port-to-substrate parasitic capacitance will also be increased. Then LC resonance will make this one, the self-resonant frequency, reduced very much. It's up to you. Okay. Anyway, this is some kind of models. Yeah, just have a look by yourself. Again, I am an IC designer instead of device engineer. I pay no attention to this. If you are interested, please have a look at the paper by yourself. This is the model for the taped transformer, and this is for the stacked with some kind of diagonal displacement. Okay, for the authors, to have such kind of analysis is really complicated. So they try to simplify the analysis by replacing the wires by a simple plate. Yeah, hollow plate. That's it. Okay. In this way, the analysis will be reduced very, very much. Anyway, they can have some kind of simulation according to aesthetic of the other software, ADS of the others, okay, to check such kind of simplification doesn't have too much impact on the simulation result, hopefully. Okay, that's it. So anyhow, you can see for such kind of displacement, the more displacement, the less K, right? Yeah, intuitively, I think that is reasonable. That's it. Good enough. Okay, that's it. So again, you need to have some kind of trade-off between the K value and the port-to-port parasitics, blah, blah, blah. Okay, the more displacement, again, the less K, but also the less port-to-port parasitic capacitance. Then you can get higher self-resonance frequency. It's up to you. OK？ 不论如何啦哈，就是说，他们把这个分析，因为这种一大堆线两层的那个电感，然后各自的绕线都一塌糊涂的复杂这个对他们来讲基本没办法分析了哈，所以作者就把它看成两片金属片啊，中空的两片金属片啊，这样的话他们的那个这个分析的解析的那个复杂度可以下降4的 n 次方倍啊哈，不过当然做起来较不准啦哈，希望就讲经过他们的那个模拟软体或是商业软体希望这个用这种简化的模拟出来的结果跟其他非常复杂模拟的结果不会差太多了哈。Anyway, anyhow, you can see 你们可以看到我既然把中文跟英文混在一起好啦，就是讲第二款这个位移越多，上下的那个电感位移越多的话，当然啦，你的那个它们中间的那个K 值就会越来越少嘛。这闭着眼睛想这个太大，所以直觉上它是对的了哈不过天底下没有白吃的午餐了，就是说位移越多K 值变得越小但它的好处是说这个一次测跟二次测它们中间的那个杂散电容也会相对的变小相对变小就是它自我共振的频率会提高，就是这样啦天底下没有白吃的午餐了It's all up to you. You need to make the final decision. How much displacement between the primary and the secondary coils as you like. I don't care. This is some kind of transformer layout example also to my memory from Berkeley Wireless Center. Yeah, you can see they have such kind of symmetrical layout and also have the center taped layout to the secondary part. Okay, here, yeah, in the middle, that is for the center taped port. Okay, anyway, this is some kind of cross-sectional view for their simulation. They are so talented for such kind of transformer simulation. They composed their own new software called FastTravel. However, to my memory, it is not open to the public. If you are interested, maybe you can write an email to the center to check whether or not they would like to provide this software for free to you. Okay, yeah, just do it by yourself. Anyway, they have such kind of model, and you can see for the model after measurement and the simulation, you can see both are quite close to each other. Yeah, I guess less than 9 gigahertz. They fit each other very, very well. See? Till now, for humankind, I think to the most we focus on around 5 gigahertz. We still not touch 7 gigahertz for commercial operation, right? So it's still quite safe to use such kind of model along with such kind of software because it provides very good simulation result, which is quite close to measurement result. The accuracy of the model and the software is fantastic. All right. And for the experimental setup, anyway, that is for your reference. This is some kind of diphoto, and you can see, see what? To the boundary, they have such kind of guardrail, and below it, you can see they have GPS, right? PGS, sorry. Pattern grounded shield. Pattern ground shield. Okay? Yeah. And again, you can see the nice for PGS and the inductor. they are perpendicular, they are orthogonal to each other. That's it. Finally, I would like to share one of the papers from my junior. He graduated from the same department, NTUST, but studied in Santa Clara, UC Santa Clara, and finally worked for Intel company. Yeah. Anyway, this is my junior. What is the motivation for the paper? Intel also focus very much on RF circuit for the modem, for LNF, blah blah blah, mixer, all of them. But they figure out that for such kind of inductor for RF chip, actually they figure out that the lifespan was much shorter than their expectation. Yeah, something wrong with their design. So after some time for operation, yeah, the chip became malfunction. So the consumer complained very much, and Intel needs to fully cover all the expense, right? They need to have some kind of free replacement, blah blah blah. They are curious why. Is there anything wrong with the whole RF circuit? But finally, they check the microphoto and figure out something wrong with the inductor. Yeah, according to metal migration, I told you in chapter 4, the smallest chapter, but even the chapter is so small, it still carries some very important idea for value mechanism, right? So this is what they saw for such kind of microphoto. They need to figure out what's going wrong. And finally, they see that the metal line actually become void here. Yeah. For example, why? From the beginning, you can see the metal line is so long, but according to the electronics flow, they collide with the metal lattice and gradually push the metal line to the right according to such kind of collision. So after weeks, months, or years of operation, gradually the metal line is pushed to the right, and finally no connection here to make the chip malfunctional. 讲简单一句话啦，就是 metal migration 造成的啦吼，因为伊的电子流向迄边嘛，意思讲伊的电流是向这边啊，日积月累的一直 K 这个自由电子一直撞晶格，然后就把因为是这个叫 metal migration 嘛，一直把那个金属线往外推到最后结果叫做断线断线晶片就敲敲一掉 Intel 就去用卖啊，对不？伊都要赔所有的那个使用者啊。甚至 Apple 也会告他，如果 Apple 是用他的 RF chip 的话 ，so Intel needs to solve the problem. Yeah. Eventually, metal line breaks. Oh, the RF chip, simply become malfunctional, or it doesn't work at all. Right? All the cost needs to be fully covered by Intel. Anyway, anyhow, if electrons flow in that direction, then you will see here and there will face the challenge, will face the serious impact from metal migration. On the contrary, if it flows reversely, then here and there needs to face the challenge, right? So anyway, anyhow, it happens around underpass, okay? According to current crowding and collision with the metal lattice. Yeah. So they have another microphoto to make sure the assessment here is correct. You can see, wow, the metals for such kind of underpass, actually, the quality is worsened very, very much. if you have a look at the top metal for the inductor, nothing wrong with the metal 9, right? But you can see here, here, and there, it has a lot of holes according to metal migration. Wow. So, what is the cure? What is the solution? Very simple. Yeah, you need to have the so-called metal reservoir. Okay. Anyway, that is what you need to do, because from the beginning, of the microphoto, you can see this portion become void. It becomes empty, right? So to solve the problem, you need to have extra layout here. That's it. Some kind of expansion for such kind of metal 9. That's it. A very simple idea. After you know the cause, and then the cure is very simple, right? But India still spent a lot of money to apply patents around the globe. To my memory, more than 10 to 20 countries. Yeah, after my junior figure out the problem and had such kind of recommendation for his company, then Intel applied patents around the globe to protect the idea, to protect such kind of innovation, right? To be honest, you don't need to be Einstein. No, if you know it is the problem, right? I think most of you or many of you will know how to solve the problem. So you need to be the first to know the problem and solve it. Then your company can apply the patent, and after that, the company will make a lot of money. You too. Got it? Got it? Okay, so you can see after the new reservoir, you can see with reservoir and originally without reservoir, the time to failure is increased substantially. By how much? 3 times to my memory. Okay, so anyway, there's some kind of 3-dimensional view. Yeah, they have extra reservoir, to make the lifespan much longer than before. That's it. Okay, and this is the microphoto. Yeah, again, it happens for such kind of underpass, right? So you only need to have such kind of reservoir, to both ends of the underpass. Good enough. Okay. Yeah, anyway, that is some kind of zoom in view. That is the whole view. And after that, as I mentioned already, 3 times more for the lifespan. Yeah, 3 times more for such kind of time, average time to failure, with and without reservoir. Bingo! Fantastic. Yeah, this is some kind of model. Okay, anyway, nothing is free. You need to pay for it because you have extra layout for such kind of reservoir. Then a little bit more parasitics here, but after measurement, you can see less than 1% increase in such kind of parasitic capacitance. So not much impact on the overall performance, right? About the same performance, but the lifespan is 3 times longer than before. Wow! So that is the power of the patent. Again, that is the power of our layout patent with such kind of very simple idea, right? You can increase the lifespan of the chip for 3 times. Gosh, if you would like to increase the lifespan for the same amount with new circuit design, I think maybe it is some kind of mission impossible, right? But with the help of very simple idea for layout, you can make it fantastic, fantastic. So again, don't look down to layout. To be a good engineer, you need to be good at both. I mean, IC design and layout. Pay attention to this. Pay attention to my recommendation. That's it. Okay. Yeah. A very simple conclusion, right? Yeah. This concept can be applied to any kind of IF technology and processes only if you need to face mental migration. Then the simplest cure is to have such kind of extra mental reservoir. That's it. Simple to test, but powerful enough. Bye. That is the end of the chapter.